Okay, so first I want to say that I'm very happy to be here to celebrate Philippe's birthday, very honored as well. I'm a great fan of the small part, in fact, of Philippe's work that I am familiar with. There's still one thing I'm not entirely happy with, I have to say, which is this old-fashioned means of transportation. So wouldn't that have been a very lovely poster for this conference? Okay, so anyway, so I think I met Philippe for the first time in '95 at a conference in SIRM entitled, what else, Combinatorics and Physics. And from the following years, I first remember the Meander papers. At that time, people used to send each other nice, flashy preprints. So that's your third Meander paper with the incredible asymptotics for the number of meanders. And then again, a few years later, the poor combinatorialists had to realize that these physicists were also extremely good at finding wonderful combinatorics on maps, and these were the BDG papers, Boutier di Francesco 60th, on counting maps with trees and so on. So that's my idea of Philippe playing with the meanders and maps en même temps. Okay, so my talk will be about maps precisely, and this is a joint work with Andrew L.V. Price, who's somewhere. Andrew, where are you? Ici. And I will first focus on these quadrangulations, hard to say. So what's the pointer? Okay, I have to get used to that. Okay, on Earth, the colors are so bad. That's a disaster. So I claim it is three-colored. So I will start with a definition of maps. So a map is just a connected planar graph. Is it better? Yeah, maybe. So in fact, a multigraph, you allow loops and multiple edges as well, and you give it with one of its proper embeddings in a plane. And you take them up to continuous deformation because you want to just have not combinatorial object, not continuous. And what you can find in a map, well, you find vertices, which have various degrees. So this one, for instance, has degree 5, because the loop counts twice. You have, of course, edges. And what is making this noise? Where's the microphone? Is it okay? Can you hear? Okay. I hear something that's unpleasant, but maybe if you don't, that's fine. And and then we have some components that a graph would not have, namely faces. So these are the, yeah? Away, just away like that? Is that better? To me it is. Okay, thank you. So that's a face, that's a component of what's left if you delete the edges. And the faces have also a certain degree, which is the length of the boundary, here 3. Now, when we count maps, we hate having symmetries. And so in fact, we count objects that do not have symmetries by considering rooted maps. And by this routing, I mean that we choose in this outer infinite face a certain corner. It's still noisy. I don't know what's happening. A certain corner between two edges, like this one, for instance. So that's a rooted map. And as soon as you have a root corner, you can also define the corresponding root edge and the root vertex. And this outer face, infinite face, is also called the root face. And its degree is the outer degree. So here we have degree 1, 2, 3, 4, 5, 6. Maybe, is it this that's making the noise? It's okay. But Rick, here's the problem. Sorry?
I guess that it is the wind of the breeze.
Oh, okay. I should stop breathing, you mean? Oh. Makes life hard. Okay. So in addition to these general planar maps, we will consider subclasses for instance, triangulations where, well, all faces have degree 3, including this strange little face here. Oh. And then I let you guess what quadrangulation is. All faces have degree 4. Now, one convenient tool when you play with maps is duality. That's big. So it's a transformation that exchanges faces and vertices. So you start from a map and a black one, and then in every face, here you have 3 faces, you create a red dot. And then you join these vertices. Ouais, mais okay, let's try like that. Can you still hear me? Well, okay. So you then for each edge of the original black map, you create a new edge, a red one supposedly, that crosses it and joins these 2 adjacent vertices. So that's the dual. So here I started from a black quadrangulation, which means that here on the right in the dual, I get vertices of degree 4. And such maps I call 4-valent or quartic sometimes. And finally, as you've seen in the title, we want to color our maps. And so here we just consider proper colorings, which means that if you have 2 neighbor vertices, they get different colors, and you fix the number of allowed colors. Here it would be 3. So for those of you who've never seen, if there are such people, some results in map enumeration, I will show a few, starting from what is probably the oldest one by Tat, the father of maps in combinatorics. So if you choose to take n edges, there's only a finite way to assemble them to form a map. This number is m of n, and it's given by this wonderful simple expression with a central binomial coefficient here, with this asymptotic behavior, some mu to the n to the minus 5 halves. This is an exponent that you'll see on and on. An equivalent way of describing this result is by giving the corresponding generating function. So this is a formal power series in some variable t, and the nth coefficient is this number. So I call m this series, and for this problem, it has a nice algebraic expression with a square root here. And in particular, this is an algebraic series, and by this I mean that it satisfies a polynomial equation here of degree 2. And there's a third property, which is very important combinatorially, which is that the underlying curve, if you want, in T and M, admits a rational parametrization. So here, for instance, if you write T as this fraction in A, so this defines A as a power series in T equivalently, which counts some trees, then it can be proved that the series M is A minus TA cubed. And so there's a very nice combinatorial explanation for this in the census paper by BDG. Okay, so that was a long slide, and from now on, when I will show you map counting results, they will be summarized like that. The generating function of maps counted by edges is algebraic, degree 2, with a rational parametrization, and this asymptotics. Now, as I wrote, this is a very typical result. So for instance, if you look at those triangulations, their series T is algebraic, degree 3, rational parametrization, and what's important, same asymptotics. Now you may remember that we want to count colored maps instead. So maybe we can start with 2 colors. Well, then if you take all bicolored maps, again counted by edges, series is quadratic with a rational parametrization and this exponent. Okay, so we keep telling the same story. However, I would say that this is a fake coloring problem because first, if you have a map, it is bicolorable if and only if all faces have even degree. And in addition to that, if this holds, like here, well, once you've chosen the degree of the root, there's a single choice for the whole coloring. So it's not a true coloring problem. We are just counting maps with the faces of even degree. But still, that's a nice result. So let's keep to 3 colors instead. And so then we can color triangulations if we have 3 colors. And again, the series is algebraic, degree 2, rational parametrization, and same asymptotics. But again, this is a fake coloring problem, because this time it's not too hard to see that triangulation is 3 colorable if and only if this time all vertices have an even degree. So again, we're counting a family of maps which has a nice generating function, but it's not really a coloring problem. And you may have noticed that in addition, this result is the same as on the previous slide, and there's a good reason for that, because if you, so you can't see the colors, but if you delete, say, the purple vertices here, what you get is just a bicolored map, and so this is the same problem. So now I come at last to my first authentic 3 coloring problem, and this is a result that we proved with Olivier Bernardi some 15 years ago. So now you take all planar maps, you want to 3 color them, and then you find something that's algebraic, this time of degree 4 with a rational parametrization and a good old asymptotic behavior. Now there's a difference with the previous results. So all the results before are now completely understood at a combinatorial level using constructions based on bijection with trees and so on. So that's a topic on which Philippe contributed a lot. This result is so far, I would say, complicated and mysterious. So in particular, we have no bijection with trees, and there must be some. And finally, the maps that are mentioned in the title of my talk, they are the 3 colored quadrangulations. Maybe I could get rid of this little thing here. Attends, voilà. So, well, you can't see really the colors, but so if you think that I keep showing the same slide with small variations, it's time to wake up. The generating function of these 3 colored quadrangulations is not algebraic. So my vague ideas of universality are completely wrong. And however, it has a nice parametrization in terms of a series A that satisfies this. So if you write T like that, the variable, then the series of 3 colored quadrangulations is essentially T minus A. Now you may wonder about the asymptotic behavior, and again, everything is lost. Instead of this minus 5/2 exponent, you have this n log n squared at the denominator. So really something happens here. Now the next thing I want to do is to convince you that this coloring problem is in fact very rich, thanks to 3 main bijections that transform it into other interesting problems. So the first one, yeah, sorry, that's Euler. That's Euler, that's not Philippe. So luckily now, so I take one of these 3 colored quadrangulations and I replace colors which you can't see by numbers that you can see. So the colors are now 0, 1, 2. And so if you have one of these objects, if you look at one edge, what happens is that the labels along the edge, they vary by plus or minus 1 mod 3. This is a 3 coloring. Now what you would like to do is to construct from this the same quadrangulation, but with labels in Z now, not mod 3, that would satisfy the same conditions. That is, here, for instance, I have, when I go from this vertex to this one, I have an increment minus 1, mod 3. So I would like to write a -1 here. I want to be in Z rather than in Z3. So this happens to be doable in a consistent way, which is not obvious. So for instance, here, if I follow this chain, I start from 0, and mod 3, I do -1, -1, +1. So here, I want to have 0, -1, -2, and then -1. But happily, if I follow this edge instead, I start from 0, I want to have -1. Whew, aren't we lucky? This is what we obtained. So what you get on the right, I would call a height model. So that's a quadrangulation with some heights on the vertices that can be positive or not. And this is only doable because we have quadrangulations. For instance, if you take this small three-colored triangulation, and okay, you put 0 here, here you keep the 1, here you have to put -1, but along this edge you have an increment of 2, and you're not happy with that. So that's the first bijection that appeared first in this paper by Andrew and Tony Goodman. And from now on, I will forget colorings and stick to height models on quadrangulations. Second bijection, well, it's just duality. So I've shown you already how to construct the dual of this quadrangulation, this supposedly red map. And now you want to record on the dual the edge labels, the heights. And there's a rule to do this, so you will orient the edges of the dual according to a certain rule. So for instance, here, I go from I equals 0 to I plus 1, so I orient the edge like that. And again, this can be done in a consistent way, and what you obtain is a quartic map. All vertices have degree 4, and an orientation of the edges that is Eulerian, which means in our language that at every vertex you have as many incoming as outgoing edges. So in more physics terms, it would be the 6-vertex model, but on a map, on a random lattice, or rather a 2-vertex model, because on maps you have only 2 different types of vertices. My third bijection, which is not mine, is due to Ambiel and Budd. I was unable to find the little bar here, sorry. It's something that's less simple than duality. So you start again from the quadrangulation, and now you will create a new edge, which is blue, in every face, following again a certain rule, depending on the labels, and this is the direct generalization of Gilles Schaeffer's work and the bijection that was already mentioned. And if you do this, sorry, wrong direction, you get another interesting object, which is just an arbitrary map, there's no degree condition, with labels or heights on the vertices. And now it is weakly labeled, meaning that along one edge, the labels, they differ either by 0, +1, or -1. Sorry? Yeah. Yeah, sure.
You draw graphs. Can you associate triangulation of surface with that? So all your vertices are 4 values.
Yeah, yeah.
This interchanging orientation. It's true that you can always make it like incoming, outgoing, outgoing.
I'm sorry, I couldn't hear precisely because...
Is it true that orientation of edges in any vertex you can always make like interchanging, like outgoing, incoming, outgoing, incoming?
So these are some vertices that are of interest that we will call later alternating, but there are vertices of different types.
Not all vertices.
Not all. So for instance, if you take the one at the top, you have...
No, but here you can flip this loop so that it will become...
No, if you take the one at the top, maybe this will answer your question. You have out, in, out.
Yeah, but you can flip the loop and it will become alternating.
Oh, so you mean if you can only have alternating... I don't know. I should think of it.
Just my question is, if it's alternating, then it might be related
Yes. Yeah. Yeah.
You can always make it at a rating because the V's are all even, so it is phase to colorable and clockwise, counterclockwise arrows. So I think.
Okay. Yeah. We'll see a version of that later, I think. Okay. So our third object is these weakly labeled maps, and we can again apply duality with this rule that an increment plus or minus 1 gives an oriented edge. And if you have just a 0 increment, you don't orient the edge. And what you get here is a partial Eulerian orientation, meaning that some edges are oriented, not all. And at every vertex, you have as many in as out edges. Okay, so now in terms of counting, here we were interested in the number of faces, say, and there's natural corresponding parameters in all these three models. Now, if you choose to focus on one of these models, say this one, there are indeed additional statistics of interest. And for instance, here, you could decide to count also to record the number of these alternating vertices, where the orientations alternate around the vertex. And again, this translates into interesting things, interesting statistics on the other models. And for instance, here, if you forbid alternating vertices, this means that here you are forbidding non-oriented edges, so you have a complete Eulerian orientation of a map. So that's nice. And on the contrary, if you want all vertices to be alternating, this means that no edge is oriented here, so you're just counting all maps, it seems. And talking about this model, so here we have maps with orientations. Maybe it's natural to look at the number of vertices as well. And again, this translates into something in these other languages. So from now on, I will focus mostly, I think, on this version. So quadrangulations with heights, counted by the number of faces, the number of bicolored faces, so they are those that have just two labels, like this one. There's just 0 and -1. And also the local minima, which are the vertices like this one, whose neighbors are higher. And so I want to put all this in a big generating function, which I call Q, so which records faces, bicolored faces, so that's a new variable omega, and local minima. So here, for instance, there's an example with the 3 faces. The red is too dark. You have 2 bicolored faces, those which I drew in red, and 2 local minima, so it would contribute this monomial to my generating function. And if you want to play with small cases, so here are the 4 labeled quadrangulations with just one face, the outer face. And you can count how many bicolored faces and local minima they have. And this will give you the coefficient of T in this series Q. So really, you have to think of this series as a power series in T, whose coefficients will be polynomials in omega and V. Okay, so now I want to mention some partial cases that have been solved earlier. So it started with papers here by Ivan Kostov, and I think also Paul Zinjustin had a paper at the same time on the 6-vertex model. So that is, you just have this variable omega for these alternating vertices. And Kostov addressed this using an analytic approach. And as I was told, it turned out much more recently that there was a mistake in this paper. And then Andrew and Paul revisited Kostov's proof more recently, and in fact found a simpler formula, again for the same case. So the variable V had never been considered before. Now, meanwhile, and somewhat independently with Andrew, we wrote a first paper that was solving these two cases. So this includes the problem, the coloring problem with this non-rational parametrization that I've shown earlier. And more recently, so in a paper that should come out soonish, hopefully, we addressed the problem with both variables omega and v. And among earlier results, I want to mention this paper by Andrew and Tony, where, among other things, they predicted what would be the growth constant, the exponential growth constant in these two problems. And this was, in fact, a key step in guessing the whole solutions and then proving it. Okay, so now I somehow told you already that these partial results, they come in very different types. So this one I've already shown. So that's the 1-1 specialization that we solved with Andrew. So I told you if you write T like this in terms of a series A, then the series of any of these objects that we've seen is T minus A. Now, if you want to include the omega parameter, as in Kostov's work, the story is much more complicated and looks very different. So the first thing you have to do is to introduce this variant of Jacobi's theta function. So that's a series in a variable q. There's also this variable z. And I tend to drop the q in my notation. Okay, so that's just a definition. And now you will parameterize this omega and t. So omega you write like this. This is harmless. And then you introduce a series q, that is, will be a series in t, depending also on alpha, such that you can write t as this combination of theta functions and their derivatives. So the notation is misleading because you can't see any q here, but you have to remember that the q is in the theta function. And the derivatives here are taken with respect to z. Okay, so I claim that this defines a series q. And then you introduce a series A, which is expressed like that in terms of this q. And then finally, the series for quartic Eulerian orientations with this weight omega for alternating vertices is T minus A. So you see there's a big difference with the case where omega is 1, where we didn't have these theta functions and so on. So the only thing that you have in common is the expression q is T minus A over T2. And in fact, it's not obvious at all to prove that if omega is 1, then T and A are related by that. But this is something that Andrew and Paul did in their paper. Okay, so in the final part, I want to show you some ingredients of what can be done for this problem and some results as well. So first, I would say that very roughly speaking, I should avoid dark colors. Whatever you do, you end up with functional equations for the series of these labeled maps. Whether they come from from matrix integrals or from direct combinatorial arguments. And then, of course, you have to try to solve these equations. And sometimes this involves complex analytic tools and some assumptions like this one-cut lemma. And in our papers with Andrew, I call our approach algebraic just because, not because the results are algebraic, they are not, as I said, but because we are just playing with formal power series without any mention to complex analysis. And in our first paper, there was a lot of guessing as well. Now, for those of you who've never seen equations for maps, I want to mention three typical features that these equations have. So say you want, for instance, to count quadrangulations without any color, just all quadrangulations with n faces. Then, very often, you will be led to consider more general maps, like here, maps in which finite faces have degree 4, but the outer face can have any degree. So I call them near quadrangulations. And then given this new degree of freedom, this outer face that can be big, you need to record this outer degree with a new variable in your generating function, which is often called a catalytic variable. So say some y. So here you have t for finite faces and y for essentially the outer degree, which is always even. Okay, and then the third ingredient is there often occur some operators that extract from series the monomials that have positive powers. So I want to illustrate this with precisely this problem. So here's a schematic decomposition of near quadrangulations and the corresponding equation. So we start from an initial condition, so there's no finite face, that's t to the 0. The outer degree is 2, and given this convention, this gives y to the 0. That's a simple tree-like case, which gives rise to a square in the functional equation. And the interesting case is this one here, where so on one side of the root edge, you have the outer face, and on the other, you have this finite quadrangle. So what you do in this case is simply that you erase this edge, and you get a smaller map, which is also a near quadrangulation. And then you can, of course, go back to the original one in a unique way. However, this blue thing is not allowed to have outer degree 2 because you would not be able to do that. When you create this edge, the outer degree decreases by 2, and you don't want to have outer degree 0. And so the division by y is here because you decrease the half outer degree by 1, and this is just selecting the cases that are combinatorially meaningful. Now, if we return to our more complex problem of labeled quadrangulations, it seems that you cannot really avoid having not one, but 2 of these additional variables. So an x and a y. And so what we did in our more recent paper with Andrew, so we worked out new combinatorial decompositions of maps. I'll show you a bit of this. Ended up with equations with 2 catalytic variables. And for the first time, we were able to derive a characterization of the series that involves only one of these additional variables. And then we are verifying on OneDrive. I hope it will be happy. And then, without any guessing, we could derive from this characterization the solution in 3 one-variable cases. So the first one is a Kostov's case, and then the cases where omega is 0 or 1. So what I will show you is some little glimpses of these 3 boxes. So starting with, it's not moving anymore, probably because it's busy with the OneDrive. My turn, yes. So I will start with a bit of combinatorics to see a piece of some functional equation. So I'm considering a class of labeled maps with differences plus minus 1 along edges. Now the finite faces, they are quadrangles, but the outer face can have any degree. And in addition to that, we have on this outer face some Dobroshin-like boundary condition, namely, if you start from here, you will see first an alternation of 0s and 1s, and to a point, this changes to an alternation of 0s and minus 1. Okay, and we would like to cut these beasts into smaller and simpler pieces, if possible. So the first thing we do is that we start from the root, and we look at the submap, at the maximal submap that contains this, is connected, and has only non-positive labels. So this I take, this I don't take, it's positive. So these are the purple edges here. Now we take our scissors and cut around this piece, and we put it aside. So it's a nice piece in the sense that now the boundary consists of 0 and -1s only. Now we return to the bigger thing, and we're going, so you see in this piece, we may have captured some vertices with positive labels, but that's fine, we're happy with that. And then what we do is that we just contract all this purple piece into a single vertex that will be labeled 0. So now if we imagine that, for instance, what will happen to this quadrangle? So these 3 labels will be contracted into a single one and grouped here. So this means that this quadrangle, which has a corner labeled -1, will in fact become a digon. So we create digons, in fact, for every outer corner labeled -1 in this purple map. So there's 3 of them, and I just want to give you an idea. So you get 3 of these digons, which are all attached to the root vertex and come from the contraction of these kind of boundary quadrangles. And that's also a simpler map. Now the outer boundary consists of 0 and 1s only. Now imagine we want to go backwards. So we start from one of these things with digons. I don't want to give any precise definition. Say it has d digons. And I can take one of these as well. Now what I want to do is to reopen these digons, form quadrangles with them, and spread them around this purple map. But in order to be able to do this, I need to have sufficiently many corners labeled -1 here. And what this means is that I want that the outer degree of this map is at least 2D. And if this is the case, you can indeed build one of these Dobroshin map. And if you think in terms of power series, so assume we have a blue series B for these things with a variable x that records digons, the number of digons. Here we have some purple series X, P, like purple, with X recording half the outer degree. Then this condition that the outer degree should be at least 2D translates into the fact that we're going to take the product of these things, so B at 1/x, and just take the part with positive or non-negative exponents. So this is hand waving, but this is another occurrence of these positive part operators. Yeah.
The power of x is the 0-1 boundary, the length of the 0-1 boundary originally?
It is true. Yes, it is. Let's see. It will be the number of -1s left in the, and the other catalytic variable is in fact the number of 1s in the Dobroshin map. Yeah. Okay, so that was my combinatorics part. Now I just want to show you, this fits in one slide, what is this characterization that involves only one of these catalytic variables. So here is how it looks. We claim that there exists a unique formal power series in T, whose coefficients involve our 2 variables omega and v, of course. And in terms of the catalytic variable x, we allow Lorentz series. So in the coefficient of t to the n, you will have a finite number of negative powers of x. Okay. We call M this series, and there's 4 conditions. The first one tells you that M should be a multiple of t. No constant term in t, okay. So maybe M is t. That would work. But there's a second condition. that tells you that if you just look at the monomials in this series with the x to the minus 1, you should find not a big series, just TV. Okay, so maybe m is TV over x. That would work. Not too complicated. There's a third condition. Namely, which is a bit strange, that this m, this series m, should be an involution. M of m should be x. And aren't we lucky? This one works. 1 over x is an involution. Okay, so maybe we have it. Well, there's a fourth condition. And the fourth condition clarifies a bit what you are allowed to do. So I told you that the coefficients were Lorentz series in x, but not too much, in the sense that if you form this quadratic polynomial in M, then you shouldn't see any negative power of x in that. So this thing should be a formal power series in T and x. And so this doesn't work. There are still negative powers of x if you take this, and the only series that works is this one. So in fact, the coefficient of t to the n is a polynomial in 1 over x and 1 over 1 minus x. Okay, so that's an interesting result, but it's not related to quadrangulation so far. And so the final point is that this series M, we introduced it with a combinatorial description in terms of as counting certain labeled maps, and the series that we want that counts labeled quadrangulations is the coefficient of x to the minus 2 in this series. So that's a strange thing, but at least with just one catalytic variable. I choose the letters so that it is t minus v.
Morally. Like before, you said all the time, this is a t minus v. T minus a, sorry.
Yeah, t minus a.
There's not the same t minus
a. On the final slide, we'll have a t minus a. So far, we have no a. And so precisely the last thing I want to do is to specialize this quadrangulation to omega when omega is 1. And without any guessing, then we will get a new result, in fact. So here I'm just rephrasing my 4 conditions when omega is 1. And then what you can do is somehow massage these 2 conditions here. And what you get is that this thing, in fact, doesn't depend on x at all. It's just a series in T. And okay, so then we don't know what is this series A. We just know that it does not depend on T. So we solve M in terms of, sorry, it doesn't depend on X. Thank you. So we solve it for M. Okay, we know how to do that with the square root. And then we inject this second initial condition, and it determines A. And we get a new result, which is reminiscent of our first result, but now we have this v variable. So that's a parametrization, well, not really, of t, because there's t here. So that's the defining equation of some series A. And then Q is again expressed in terms of t, v, and A like that. And then we've done the same when omega is 0, and there we are counting Eulerian orientations of general maps. So that was the problem that was in the southeast corner of my slide much earlier. So we're counting these orientations by edges and vertices. Okay, so there is much more to say. My feeling is that we are just halfway in the understanding of these label quadrangulations. There's a very nice result by Andrew here on the height of a random vertex in one of these quadrangulations. But I will skip this, and I just want to finish with my birthday present for Philippe. You can play with it with your friends. I mean, you choose. So what our results, or some of our results, mean is that there exists a bijection. We don't know which one. So on bijections between, on the left, labeled quadrangulations, so we know what they are, counted by faces and these local minima, so like these red things, -1s. On the right, we have designed a class of trees that is counted by the same series. So they are plane trees. The nodes have degree 2 or 1. There's a notion of charge. At every vertex you have a charge, so this is the terminology of the first census paper, and the definition is not so different. So to compute the charge, say at this node, you look at the corresponding subtree, and you take the difference between the number of binary and unary vertices. So here that would be 2, here it would be 1, for instance. And you want trees that have charge 1 at the root. You forbid subtrees of charge 0, and you're counting them by leaves and left leaves, like these two. And our results say that these things are equinumerous. And there's a suspicion also that local maxima here become right leaves, which would be nice and symmetric. Okay, and I stop with this cadeau. Merci. Thank you for your attention.
Thank you very much for this nice talk. Are there some questions? Yes?
When you write M of x, what's the meaning of substitution for hypothesis?
Yes, so what happens, can I get back to this? Yeah. So with this condition, it implies that if you look at the coefficient of t to the n in M, so it is a Lorentz series in X, and the valuation of this series is -n or more. So you don't have two small powers of x in the coefficient of t to the n. And with this, you can check that the substitution here is well defined. Everyone is hungry.
I have just a naive question. You had some elliptic functions coming out.
Yeah.
Are there other places or maybe more general kind of elliptic functions that could come out or something like that?
So I think you know better than I do that many elliptic functions come out in some solution of map problems. A number of them were solved here. Also in some counting of paths, lattice paths recently, confined to a cone. And if you look at this problem with the two variables, we have a description of the solution in terms of a function that should satisfy an equation like a non-linear version of what the theta function satisfies somehow. So there's a generalization with V of the elliptic solution, but we don't know what the corresponding complex analytic function should be, but we have a characterizing equation for it.
Okay. Any question? Okay, then thank you very much.